Welcome back, Algebra 1 Bulldogs, to week 4 of distance learning. Today is Monday, April 6th. This is your Monday video. Before we get started on your notes, I want to explain to you a little bit how things will work from here on out. Math is releasing new instruction on Mondays and Wednesdays. So every Monday and Wednesday, you will get a new video lesson from me with some guided practice. Sometimes I will leave you with some problems to try before the next video comes out, and we will start that next video with reviewing that work that you were given. And then on Fridays, you will have some sort of assignment or assessment that is due. So this week, because we're a shortened week, Monday, today, I'm giving you some new instruction in this video with some guided practice. Wednesday, we will do the same, and then you'll have a short assignment that will be due by the end of the day on Thursday. When we come back from spring break, we'll go to the regular Monday, Wednesday, Friday section. You'll want to make sure you check the news feed and also the mandatory resources section of Google Classroom, because in those spots I have posted my permanent student support session schedule for you to take a look at. These are the sessions that are scheduled on Tuesday, Wednesday, and Thursday to help you with this distance learning material. It's a time for you to pop in and connect with your fellow classmates and also to ask me questions if you have any questions on the material. If you feel like you need to schedule a session with just you and me because you want to talk about maybe something with your grade or how things are going in the class, we can do that on Mondays or Fridays by appointment. You can send me an email and we will set that up. Couple reminders as we go through this week. First of all, on Wednesday, you have your factoring trifold project due. That is due by 11:59 p.m. What you will do is take a clear picture of both sides of your project, save that picture to your drive, and then through Google Classroom you can upload that picture and turn it in. The other thing I want to let you know is that in Google Classroom, I have created a tab that says Quarter 3 Missing Work. You should be checking PowerSchool this week to make sure all of your assignments for Quarter 3 have been turned in, especially those that were assigned, collected, and graded before we were on this mandatory break from being in class together. If you find that you have any assignments that are outstanding from that time period before the schools closed when we were still in class together, you can turn it in through that tab. I've created it as a generic assignment. The due date is at the end of the day on Wednesday this week. Say you have a set of problems from the book that you never finished and you never turned in, and it shows as a 0 in PowerSchool. You can either find that completed assignment in your binder, or if you need to still do it, complete those problems, scan and upload the work into Google Classroom through that tab and turn it in that way. If you have any questions about this, please don't hesitate to send me an email and let me know. So besides working through the notes through this video, this week you're also working on finishing up the factoring project by the end of the day Wednesday, and also checking PowerSchool for your Quarter 3 work. All of the work that you did throughout the past 3 weeks will factor into your third quarter grade, and you will start to see those grades updated in PowerSchool this week. If you have any questions, again, please let me know. Let's get started on our notes for these next two sections. We're going to be talking about 3 different special cases with factoring. And the first special case is when all terms share a common factor. Sometimes at the beginning of the factoring process, all terms in an expression will share a common factor. So first let's talk about what a common factor is. A common factor is a number or a variable that can be divided into each term of the expression. Let's take a look at the expression in example 1. When factoring, the first thing we're going to do from now on is we're going to look to see if a common factor is shared by each term. So in this expression, 4x squared minus 10x minus 6, all terms in this expression have a common factor of 2. If we take a look at each term, they are all divisible by 2, and 2 is the largest number that will go into each of these evenly. If I take 4x squared and divide it by 2, it's 2x squared. If I take negative 10x and divide it by 2, I have negative 5x. If I take negative 6 and divide it by 2, I have negative 3. So then we need to ask ourselves, well, what happens if we remove this common factor from each term? Well, the word factor itself indicates that we're multiplying. What a factor does is it takes something larger, like 4x squared minus 10x minus 6, and it breaks it down into parts that are being multiplied together. In other words, we're taking the 2 that was a common factor and we're multiplying it by what's left after we pull that common factor out. So think about what happens to each term as we divide it by 2. We had said that 4x squared divided by 2 gives us 2x squared. And negative 10x divided by 2 gives us negative 5x. And negative 6 divided by 2 gives us a negative 3. In other words, when we pull that common factor out, we should be able to take both factors, multiply them together, and end up back where we started. Think about what would happen if you took the 2 and distributed it back through the parentheses. Would you end up back at 4x squared minus 10x minus 6? And in fact, we would. The next thing we want to do after we pull out that common factor is take a look at the factors we wrote down. Can any of them be factored again? And the answer is yes. 2x squared minus 5x minus 3 can be factored using the methods that we had used last week and the week before, the methods you learned during weeks 2 and 3 of our distance learning. So we're going to go back to using an area model and our diamond problem to help us out. I'm going to take the first term, 2x squared, and the last term, negative 3, and place it in the area model on one of the diagonals. Then I'm going to start using my diamond problem by taking a look at the product of that diagonal, which is a negative 6x squared. That's going to be the product that I'm working towards in my diamond problem. I'm also going to take a look at my middle term, which is negative 5x. That's what this spot and this spot in the area model need to add to. And so that becomes our sum in the diamond problem that we are working towards. Now we take a look at the factors of negative 6x squared. The pair that's going to work for us is negative 6 and positive 1. Negative 6x times x will give me a negative 6x squared, and negative 6x plus x will give me a negative 5x. So negative 6x and positive x are the remaining 2 terms that I'm writing in my area model. Now I need to find the dimensions of my rectangle. To multiply to 2x squared, I need 2x and x. Now in the bottom left-hand corner, I also need a minus 3 to make my negative 6x, and I need a positive 1 to multiply to give me -3 and positive x in the upper right-hand corner. This means that 4x squared minus 10x minus 6 can be rewritten as a product of all of its factors. 2 times x minus 3 times 2x minus 1. In this next example, we're trying to factor 3x cubed minus 12x squared minus 36x. The first thing we're going to do again is take a look at each of the terms and decide if there is a common factor that is shared by all of the terms. Is there a number that goes into each of the coefficients evenly? And can we possibly pull out some powers of x as well? Each of these terms is divisible by 3x. The common factor is 3x. Because each of the coefficients is divisible by 3, and each term has at least one power of x to spare. So what we're going to do is we're going to rewrite that expression and pull out that common factor of 3x. When we do that, if we take 3x cubed and divide it by 3x, we're left with x squared. If we take -12x squared and divide it by 3x, we're left with 4x. And if we take a -36x and divide it by 3x, we're left with -12. One little trick you can use when you're pulling out these common factors is take a look at the numbers and letters separately. Ask yourself how each of the coefficients or the numbers in front of the variable are divisible by 3. 3 divided by 3 is 1. -12 divided by 3 is a -4. -36 divided by 3 is a -12. Then take a look at the variables. We are pulling away one of the x's from each term because this is x to the first power. So x cubed, take away one of those x's, is x squared. X squared, take away an x, is just x. And x, taking away a power of x, removes all of the x's from that term. At this point, what we need to do is we need to factor this remaining expression, or at least try to see if it factors. What I'm going to do is I'm going to pause the video. I want you to do the same, and I want you to continue factoring that expression, and then we'll come back and check your work. Okay, we are back and we're ready to check your factoring for the expression x squared minus 4x minus 12. We'll place our first term and our last term. The product we're working towards is a -12x squared. The sum that we are working towards is a -4x. The two terms that will work to give us that product and that sum is -6x and a +2x. And so the dimensions of my rectangle are x minus 6 and x plus 2. 3x cubed minus 12x squared minus 36x factors into 3 factors. The 3x that we pulled out in the beginning, and the x minus 6 and the x plus 2, which were the dimensions of the rectangle I used to factor the remaining expression. The second special case we are going to talk about in these notes are expressions that have terms that are written out of order. Standard form for a quadratic expression is ax squared plus bx plus c. What that means is we write our x squared term first, our x term second, and our constant term last. When quadratic expressions are organized and the terms are written in standard form, it is easiest for us to factor that quadratic expression. So what we want to recognize when we look at a quadratic expression, not only do we want to look to see if we can pull out a common factor, but we want to also always make sure that the terms are written in standard form. In example number 3, our quadratic expression is not written in standard form. So the first thing we are going to do is rearrange the terms so that our x squared term is first, our x term is second, and our constant term is third. Now our quadratic expression is written in standard form. Notice that the sign in front of the numbers in the original expression stay with their terms as we rearrange them. The 8x squared had a plus sign in front of it, and when I rewrite the expression, that term is positive. The 10x term had a minus sign in front of it, and when I rewrite the expression, it's negative. There was no sign in front of the 3 originally, so we assume it's positive, and when I rewrite it, it's positive as well. The next thing we want to do is take a look and see if we do have any common factors. When we take a look at each of the terms, there isn't a factor or a number that divides evenly into 8, 10, and 3. 8 and 10 both share a common factor of 2, but 3 does not share that common factor. When we take a look to see if there is a common factor of x, the first 2 terms have x's to give, but the last term does not. So we would say that this expression does not share a common factor between its terms. We can jump right into using our area model to factor this expression. I'm going to place my first term and my last term. The product that I'm working towards is 24x squared, and of course that comes from taking a look at the product of my diagonal. My sum comes from my middle term, which I can see clearly is a negative 10x. That becomes more clear to me after I rearrange my terms. I know that's what this box and this box need to add to. The 2 numbers that are going to multiply to give me a positive 24 and add to give me a negative 10 are negative 6 and negative 4x. Now I need to find the dimensions of my rectangle. To make 8x squared, I could use 4 and 2. I could use 1 and 8. I'm going to use 4 and 2 though, because I notice that neither the row nor the column has terms that are both divisible by 8. So I'm going to use a 4x in my upper left-hand corner and a 2x in my lower left-hand corner. That means I also need a negative 3 in this position to give me negative 6x, and I need a negative 1 in the bottom right-hand corner to multiply to give me positive 3, and also negative 4x in the upper right-hand corner. My expression, 8x squared minus 10x plus 3, factors to 4x minus 3 times 2x minus 1. At this point, we're going to pause the video again, and I would like you to try working through example 4 on your own. Take that expression, rewrite it so that it is in standard form, check to see if there are any common factors that you can pull out of the terms, and then continue factoring using the area model and the diamond problem. We are back. When you rewrite this expression in standard form, the x squared should be written first, followed by the minus 8x and the positive 15. Each of these terms does not share a common factor. Remember, there is a coefficient of 1 in front of the x squared. Between the numbers 1, negative 8, and positive 15, the only common factor that they share is 1. And since multiplying by 1 does not change the value of an expression, we do not pull out common factors of 1, only factors that are greater than 1. Also, the last term does not have an x term, which means they do not have a common variable that we can pull out. So we're going to skip right to our area model and our diamond problem, placing my first term in the upper left-hand corner, my last term in the bottom right-hand corner. The product I'm working towards is 15x squared. The sum that I am working towards is my middle term, negative 8x. The factors of 15 that will also multiply to give us negative 8 are negative 5x and negative 3x. So the dimensions of my rectangle are x minus 5 and x minus 3. This means that the expression x squared minus 8x plus 15 can be rewritten as the factors x minus 5 and x minus 3. The third special case that we're going to work through today is called the difference of squares. Think back to week 2 and week 3. Some of the expressions we factored during week 2 were missing a term, and we need to remember how we handled that. If you remember, what we did was we added in a 0x term as a placeholder. When a quadratic expression is missing its middle term and both of the terms are perfect squares, a pattern exists when factoring. So the first thing we need to talk about before we start looking for that pattern is, what does it mean if we're working with a perfect square? Well, perfect square is what you get when you multiply two integers by each other. For example, 25 is a perfect square because we can get 25 by taking 5 times 5. Since we've already done a lot of work factoring expressions that are missing their middle term, I would like you to start by working through examples 5 and 6 on your own and go through the normal process for factoring those expressions by rewriting the expression using 0 as a placeholder for the missing term, then use the generic rectangle and diamond problem to help you find the two factors for that expression. So for example, with 9x squared minus 4, I want you to start by writing 9x squared plus 0x, so we have that placeholder for the missing term, minus 4. You'll go through the regular process and factor it, and after each of these examples, I want you to keep in mind what we just talked about with perfect squares, and I also want you to take a look at where you started and where you ended up with factoring, and ask yourself if you notice a pattern. Okay, we're back. You can see I filled in all of the answers for you so you can check your work. If you're struggling with the factoring, you should definitely think about popping into one of my student support sessions this week, and I can help you with that. I know we're moving through the factoring part of some of these problems rather quickly, but that's because we've been working on this for 2 weeks now, and we should be pretty proficient with that skill. So if you're still struggling, think about popping into one of my support sessions this week and we can work on that together. Hopefully, after you went through this, you started to notice a pattern. What I'd like you to take a look at is what we started with, 9x squared minus 4, and where we ended up. The 3x that's at the start of each of these parentheses happens to be the square root of 9x squared. 3x times 3x is what gives us 9x squared. And the plus 2 and the minus 2 is what we would multiply together to give us the minus 4. So what happens when we factor an expression that is the difference of two perfect squares, we're taking those two terms and breaking it down into the squares that helped us get to that expression in the first place. Take a look at the 4x squared and the negative 25. To get 4x squared, we needed to take 2x times 2x. And to end up at negative 25, we would need negative 5 times a positive 5. 2x minus 5, 2x plus 5 becomes my two factors. So to summarize this idea of the difference of two perfect squares, the pattern that occurs is if we are factoring an expression of the form a squared x squared minus b squared, so the first term and the last term are both perfect squares, that factors into ax minus b times ax plus b. What I want you to do is see if you can apply this shortcut based on the two examples we just went through and explained and this pattern we just spelled out. Can you apply that shortcut to the following three problems? Can you factor these problems without using a diamond problem or an area model? Let's stop the video. You can give it a try and then we'll come back and check your work. Hopefully when you started each of these problems, you took a minute to stop and make sure that each term was a perfect square. In this problem, 36x squared is a perfect square. 6x times 6x will give us 36x squared. Negative 4 can be obtained by multiplying negative 2 times a positive 2. Therefore, 36x squared minus 4 factors into 6x minus 2 times 6x plus 2. 4x squared minus 100 is a difference of two squares as well. To get 4x squared, we would need 2x times 2x. To multiply to give us negative 100, we can use a negative 10 times a positive 10. 4x squared minus 100 has two factors, 2x minus 10 times 2x plus 10. In this last expression, 25 is a perfect square. 5 times 5 multiplies to give us 25, but 3x squared is not. To obtain 3x squared, I would need to multiply 3x times x. Because the 3x and the x are not the same term, this is not considered a perfect square. So the rule does not apply. Also, it's not a difference, it's a sum. So we would say not a difference of two squares. And in fact, if you would switch to your area model and diamond method for factoring, you would also find that this expression cannot factor using that method either. So to summarize what we've talked about in this lesson, before factoring, Make sure that the terms are written in descending power order. Highest power of x first and the constant last. For example, the expression 30x squared plus 2x to the fourth minus 16x cubed should be rewritten in standard form as 2x to the fourth minus 16x cubed plus 30x squared. The next thing we should do is take a look and see if there is a greatest common factor that is shared by each of the terms. Remember my tip of taking a look at the numbers separately from the variables. If I take a look at all of the numbers, 2, -16, and 30, the largest number that divides evenly into all of those numbers is 2. Then I take a look at each term and the x values that it has to share. The term that has the least number of x's is the last one. It has an x squared in it. So this is the most that I can borrow from each term. I can borrow an x squared. So 2x squared would be the greatest common factor that I could pull out. If I'd like to factor 2x to the fourth minus 16x cubed plus 30x squared, I should first pull out a greatest common factor of 2x squared, and the factor that is left is x squared minus 8x plus 15. The last thing we need to do is take a look at those two expressions and ask ourselves, can either of them be factored more? I'm going to take a look especially at this last factor because that looks like something that I might be able to factor more to finish factoring this expression. So I'm going to take a look at the x squared minus 8x plus 15, and I'll use my area model and diamond problem to help me with this factoring. After completing my area model and finding the dimensions of my rectangle, I can see that the expression 2x to the fourth minus 16x cubed plus 30x squared has the factors 2x squared times x minus 5 times x minus 3. To help you practice some of the skills that we reviewed and also introduced today, I would like you to try the following problems. You can work through these on a separate sheet of paper. On Wednesday, when I post the second video for the week, I will start by giving you the answers to these problems so that you can check your work. If you have any questions along the way, remember that I have student support sessions scheduled on Tuesday, Wednesday, and Thursday to help you guys out. Please stop in and ask questions about any of these problems or questions about the notes if something didn't make sense. You can find the schedule for these help sessions posted in Google Classroom under the heading Mandatory Shutdown Resources in the Classwork section. Good luck, and we will check back again on Wednesday to see how you did with these problems.